So let's revisit section 5.5. 5.5 was about use substitution to undo chain rule. If you differentiate a composite function, you use chain rule. To undo that, to anti-differentiate, if you've used chain rule to differentiate, you use something called use substitution. But before, we only worked with indefinite intervals. What if we have a definite interval? Okay? So examples 7 and 8 on page 416 in section 5.5 illustrate this. So let's evaluate the definite integral from 0 to 4 of the square root of 2x plus 1. Okay, that's the definite integral from 0 to 4 of 2x plus 1 to the 1/2 power. I just did a really big no-no. I didn't write the dx there, and that's a federal offense. That's horrible. I ought to go to calculus jail for that. This dx, you've got to write that every time. Okay. Now, this is a use substitution problem, right? I don't just have an x to the 1/2. I've got an f of x to the 1/2. Right? I can't just say this is 2x plus 1 to the 3/2 over 3/2. I could do that if this function inside were just x, but I've got a composite function. I've got 2x plus 1 instead of x. So that's when I need u sub. So use the inside function, 2x plus 1. The differential of u is the derivative, which is 2 times dx. But now we've got an extra step because this is a definite integral. Notice this 0 and this 4. That's an interval of x's, right? I'm partitioning the interval from 0 to 4 on the x-axis. But in this change of variables, I've switched it to the u-axis. Now, if x is 0, dx here. If x is 0, what's u? Isn't u 1? If x is 0, u is 2 times 0 plus 1, or 1. Okay, that x being 0 turns into a u being 1. If x is 4, u is 2 times 4 plus 1, or 9. The interval from 0 to 4 on the x-axis is the interval from 1 to 9 on the u-axis. So my definite integral is the integral from not 0 to 4 anymore, but from 1 to 9. Where does my u appear here? That's u to the 1/2, right? Remember, what's my dx? Solve for dx. I get du over 2. So the 1/2 comes out front. I anti-differentiate u to the 1/2. That's u to the 3/2. Over 3/2. I evaluate that from 1 to 9. But I can't forget there's a 1/2 out here. Okay? So that's 1/2 times, to divide by 3/2 is to multiply by 2/3. So instead of dividing by 3/2, I'm multiplying by 2/3. So it's u to the 3/2 minus 1 to the 3 halves u to the 3 halves is square root of u cubed. Square root of u is, 9 to the 3 halves is square root of 9 cubed. Square root of 9 is 3. 3 cubed is 27. You can punch that in your calculator. 1 to any power is 1. So that's 2/3 times 1. So I get 1/2. Divide 27 into 3 equal parts, you get 9. 9 times 2 is 18, minus 2/3. So half of 18 is 9. Half of 2/3 is 1/3. So it looks like I get 8 2/3, which would be a correct answer, or 26/3. Okay, why don't you try this last one? Definite integral from 1 to 2 of dx over 3 minus 5x quantity squared. Remember, we can write that as 1 over 3 minus 5x quantity squared dx. They were just saving space there. What would your first step be? Could I write that as 3 minus 5x to the negative 2? Then it becomes a u sub, right? Okay, I could combine these fractions, but I'm out of room. But I get negative 1 over 35 plus 1/10. If you've got a question on that, you can shoot me an email. One thing to notice when you're doing U sub and definite integration is that you don't go back and change the u's to x's, because these numbers you're plugging in the first problem, 9 and 1. The 9 and 1 are what? They're u's. In the second problem, I'm plugging in negative 7 and negative 2. They're u's. You plug u values in for u. You plug x values in for x. Since we're changing the numbers a, b to u values from the original x values, we just plug in those new values in for u. We don't change back to x. Now, something interesting happens on example 8. Notice when we do this change of variables, the interval from 1 to 2 becomes negative 2 to negative 7. So, we're always partitioning an interval AB. A is smaller than B, right? If you have an interval AB, A is smaller than B. But look, in this definite integral, we have negative 2 to negative 7. Those limits of integration switched on us. Look on page 385, section 5.2. Here's a definition. If B is less than A, right? Normally A is less than B, okay? Because AB is an interval. But if B is less than A in a definite integral, we define the definite integral from A to B of f of x dx to be the negative of the definite integral from, I need to say, B to A. B to A. So in other words, the definite integral from 2 to 1 of f of x dx would be the negative of the definite integral from 1 to 2 of f of x dx. In terms of a limit of a sum, it doesn't make sense to talk about a definite integral from 2 to 1, because that's not an interval. But we define what we mean by that. So we define the definite integral of f of x from 2 to 1 to be just the negative of the definite integral from 1 to 2. Back up here in example 8, when we had this definite integral from negative 2 to negative 7, I could have said that was the negative of the definite integral from negative 7 to negative 2. But fundamental theorem of calculus works just fine if the a is bigger than b or the a is less than b. So this fact here at the bottom on page 382 is something that you need to know, just so it won't look weird when you see a definite integral, say, from 2 to 1. But you really don't have to always change it to the negative of the definite integral from 1 to 2. We certainly didn't do that up there in example 8, and fundamental theorem of calculus worked out fine. I could have made that change, but I don't have to. Now, finally, use your common sense here. What's the definite integral from a to a of f of x dx? Think about that. If you partition the interval from a to a, what's the area of the region underneath the graph of f of x and the x-axis on that interval a to a? Well, that would just be 0, right? And that's a theorem on page 385.